linear operators and functionals in norm spaces. So first definition, let X and Y are linear spaces over one field, and this assumption will be every time. I don't write it every time, that we have on over one field, and map A capital from X to Y is linear operator. Okay, one field K, which is R or C capital, is linear operator from X to Y if for any alpha beta from the field X1 and X2 from the X capital, the action of operator on the linear combination equal to the linear combination of the action of operator. And when operator acts on one vector, I do not write the brackets as with analogy with matrix multiplication. But when operator acts on the linear combination, it's usually taken brackets. So, but if X and Y are normed space, we can define the norm of operator. This supremum of the ratio and supremum we take all over vectors from X capital which are not zero. Here I write three norms, but all these norms are different. This, for example, the norm in the space Y. This is the norm in the space X, and this is the norm of operator from space X to the space Y. Is it clear that this is a real norm? Yes. The norm of operator. It is easy to check that this formula indeed gives us a norm by all axioms of norms are valid. It is of course non-negative. It is zero if operator A acts on X and for any X obtain the zero element. So such operator is zero operator. And it is homogeneous for positive numbers because this norm in Y is a norm, and triangle inequality valid. So because for Y we have triangle inequality, and the supremum of the sum is less or equal of the sum of supremum. Of course, let's some notation. By these letters, we define the all linear operators. Operators from X to Y. Of course, it is linear space. We can define the sum of operators. So A, B from L, X, Y. So A plus B acting on X. It is just point action. And if alpha from field is scalar, then alpha A acting on X is alpha A X, and because Y is a linear space, this is all operations are correctly defined. Yes. And definition: operator A linear from X and Y, X, Y norm space. Spaces. A is bounded. If its norm is finite. Later we begin a theory of unbounded operators, but nearest time we study the bounded operators. And there arise a lot of tasks to calculate the norm of some operators. This formula for standard, classic formula for norm of operator is not convenient because we have, for example, if you want to calculate the norm of operator, you must take the norm in space Y, divide it on the element, on the norm of element in space X, and try to find the supremum. So let's I define some another formulas, and we prove that they are equivalent. For example, the norm with the index 1, I take the supremum on the sphere, unit sphere. And the norm with index 2 is the supremum over unit sphere. Not sphere, but ball. And the statement that all these norms are the same. These all norms are the same. Note that by definition, of course, we have some inequalities. For example, this norm is not greater than this norm. Yes, less or equal, because the ball is a larger set than unit sphere. And of course, if we take standard definition, I repeat it again, not for all x which is not 0, and put here norm x equals to 1, we obtain just the norm 1. So of course, from this we immediately obtain the following inequality. So if we want to prove the equality, so we must obtain the inverse inequalities. And how we can do it? Again, use the property of the norm. We can take inside and take outside of the norm the positive numbers. Yes. So x is not 0, then the norm of x is not 0, it is positive. I can write it in the following way. Put the norm of x inside the norm of ax. And we know that the norm of this element, equals to 1. Just we put it. So we immediately obtain that this is not okay. So we obtain one inverse inequality. Then if we take the norm 2, which is supremum on the sphere, If x is 0, we do not obtain the supremum. Yes, so it is equal the supremum all over elements with which are not 0. Because linear operator, the 0 element maps to the 0 element. And here we can make the following. Again, the norm of this element equals to 1, and the norm of this element less or equal to 1. We take supremum for all elements from the ball, but not 0. And we immediately obtain that it is less or equal to the normal. So it's the end of the proof, and the supremum on the new unit sphere is more convenient. Remark: from the definition of norm, we can obtain the so-called multiplicatory inequality. The norm of the element of operator is supremum, so it is greater or of this ratio because it is supremum for all x which is not 0, and then we immediately obtain that for any x we have a multiplicatory inequality. Okay, so the way to calculate the norm, of operator start from the ax and use some classical inequalities. And finally obtain this object. So you must obtain the norm of element x multiplied on some constant c. If these inequalities are precise, in approximately 90% of cases, the c is a correct answer. So C is correct answer for on A. But to prove it, we must show one of two cases. First case, exists X such of that it is 1 and AX equals to C. Or second, exists sequence xn equals to 1 and AXN tends to the C. If you obtain one of these, then we can conclude that it is real norm. So calculation of the norm of operator has two steps, usually two steps. Estimations above, and then the proof that this estimation can be realized. Or it is maximum, or it is real supreme. Is it clear? No, let's some example. Let some example. Let example.
Excuse me, what is the difference between condition 1 and 2?
It is not conditions, it is steps which we need to show that C is a real norm. The difference,
what is
first cases, it is just the cases. First, norm can be maximum, yes? So it is possible to, if it is maximum, you can find only one element with the unit norm and show that this estimation C is realized. But norm can be not a maximum, it can be just a supremum. Then you must find the sequence and show that these estimations can be approximated as precise as we want. So I show it in an example. Let phi is a continuous function and fixed. And consider operator A phi f just operator of multiplication. So for example, in quantum mechanics, X equals X, it's operator of multiplication in coordinate. It's operator of coordinates, so-called, in quantum mechanics. For this, find the norm. A phi acts from space CAB to CAB in class of continuous function, and B consider this operator in L2AB to L2AB. And the task, find the norm in both cases, in both situations. First, AF, just by definition, it is maximum phi x fx. And we know that the maximum of multiplication is less or equal of multiplication of maximums. So some classical equality. This is just a norm of element f. And this is some constant c. So we can see that it is less of norm of phi. So what we can conclude from this? It implies that the norm of operator less or equal to the norm of function phi in space of continuous functions. And let's take f equal identically to 1, identically constant function. Of course, the norm of this function is 1, yes? That's f0. f0 equals to 1. And the norm of a f0, just the norm of phi in CIB. So from these two steps, we conclude that the norm of operator just equal to the norm of function by CIB. So if I consider, for example, C01 and operator AF equal to X fx, then the norm of operator equals to 1. Just to this. So, and the second space B, AF square, we change the space and we must change the norm. It is just this integral, yes, because in L2 the norm is the square root of the integral of the square of the function. And we must do something with this integral and obtain only we must obtain the integral with only function f, because the norm in L2 is the integral of 1. So we can take away from the integral the maximum value of f square, yes? This is just the norm of f square in L2. So we again can conclude that the norm of operator less or equal maximum phi of x. But the example from the previous item, from item A, f0 is not convenient, because the norm of constant on the arbitrary interval AB is not 1. It is a square root of length of the interval. So this function is not useful. So to prove that the norm equal to these numbers in space L2 needs another method. What we know? We know that the function phi is continuous, yes? So there exists point x0 such that the value of the function phi at point just gives us a maximum, yeah? All continuous functions and continuous functions have a maximum on the interval, on the compact, just on the interval. Without loss of generality, you can take take assumption that this is interior point. If it is not interior, it is the end of the interval. You can take one side neighborhood. I give a picture for the two side neighborhood. So I take the intervals neighborhood. It is x0 plus 1 to n, and this is x0 minus 1 over 2n. And here I take the step function, and the length of this is square root of n. This is graph, so the graph of function is here 1 square root from n, and here is 0. Here is 0. It is graph of function of n. I don't give a precise formula. I think from the picture it is obvious what we can do. What you can say about the norm of function f in L2? Why I take such function? The norm of this function equals to 1. Yes? Because the length of the neighborhood of the x0 is just, and then calculate AFN. It is integral from x0 minus 1 to n, x0 plus n, phi of x, n, not norm, but absolute value, square, dx is a Lebesgue measure, classical, and 1 over 2. Yes? What you can say about this integral? I just rewrite it in the following form. It is just integral in these limits, because we have fn is the indicator function, but with some not one value, but square root of n. And by the middle meaning theorem, this is equal, the length of the interval is 1 over n, and we divide on the 1n square. So it is equal to, this is phi xn square, where xn belongs to our interval x0 minus 1 to n, x0 plus 1 over 2. So it equals
Why the norm here is n times phi x?
what? Please repeat your question.
Why it's n times phi x squared?
It is this interval equals to the value of the function phi in some middle points. Xn lies on the interval. It is for the middle meaning theorem. A b phi x dx dividing b minus a equals to some where constant c belongs to the interval ab. I use this theorem. If function f phi is continuous.
Why it's n times phi x?
Constant c, point c is a middle point of interval ab. So this integral equals to oh, sorry, yes, I understand your question. I special take the square root, so n, yes. Is it correct now?
Yes, yes.
Oh, yes. So thank you. So because I take a special square root to divide on just the length of the on the length of the this interval. So we obtain that it is equal to fxn, and it is 10 to the phi, the value of phi in the point x0 as n tends to the infinity. So in this situation, we must construct the sequence. So it's just two different cases. You can obtain, you can investigate operator with this property, or you can investigate operator with this property. So if you first you obtain some estimation, and then you must show that if you want to prove that the C capital is just a norm, you must check one of two situations, only one of two situations. But you must to guess what can happen with operator A. Is C is a maximum, or C is just a supremum? So first space we can find one function f0, and we see that this norm is just a maximum, not supremum. But in situation B, in another space, the same operator have the same norm, but is just a supremum. If function phi is not a constant, then the norm is just a supremum. It realizes only as a limit on a sequence. Is it clear? And notation. So again, I repeat first notation. L, X, Y, L cursive is all linear operators from X to Y, and B x, y, all bounded operators, all bounded operators again from x to y. And if x capital coincide with y, we write Lx and Bx. We write only one space. So one useful theorem, I just take a definition. First, I give a definition. A is continuous, but more accurate. A linear operator x, y, normal space. A is continuous in point x0 if from xn tends to x implies that axn tends to the ax. First, and A is continuous if A is continuous in any point x. And theorem let x, y are norm spaces, and A is linear operator. Then the following, I just use this letters for one. The following are equivalent. First, A is continuous at some point. I write in, let's say, x0. Second, A is continuous and third, A is bounded. So the continuous of operator for linear operators is synonym for the boundedness of operator from this theory. So it is the main property of a bounded operator. For unbounded operators, we can't make this limit. So the proof. This is obvious, yes? The continuous at any point gives us a continuity in one point. Yeah? So let A continues in point x0 and xn tends to the sum point x. Then it is easy to see that xn minus x plus x0, the method of shifting in linear space, of course, tends to the x0, yes, because x the difference xn minus x tends to the 0. Then our operator is continuous at point x0, so a xn minus x plus x0 tends to the ax0. Tends to the ax0. Then operator linear. So by linearity of operator, I can rewrite left side in the following way. And then from the last formula, we immediately obtain that this is object reduced in the difference in the norm. So we obtain that axn tends to the ax. So by linearity of operator and linearity of spaces, of course, the continuity in one point is equivalent to the continuity at the end in any point. Then third step of our proof, let's enumerate it. First step, second step by and third step. From 3 to 2. Let xn tend to the x, axn minus ax. By the definition of linear operation for operators, we can write it as acting on the difference of the vectors, and then by multiplicator inequality, we can rewrite it as following. This is finite, and this tends to the 0. So we obtain the continuity at any point. Yep. And the last step of our proof from 2, yeah. We know that the first property is equivalent to the second property, so we from the 2. By contradiction, let operator A is not bounded. Let assumption. Then I take the definition of the norm on the unit sphere. Then exists sequence xn, such that all x, the norm of all elements is 1 on the unit sphere, but the norm of axn not less than n. Yes, if operator is not bounded, we can obtain any value of norm on the unit sphere. Then define yn as xn divided on n. Then we know that the norm of yn equals to 1n and tends to the 0. So yn tends to the 0, but yn not less than 1. It is contradiction to the continuity at 0. For continuity at 0. That's all. That's all. So any bounded operator is continuous operator and inverse. Continuous operator is bounded. And question, when the space of operators is complete? We know that among all normed spaces, the Banach spaces are good spaces. So the following theorem, so let X, Y are normed space. Of course, on over one field, I don't repeat it any time, are normed space, and Y is Banach space. So Y is complete. Then the space of all bounded operator is complete too. Okay, yeah. So proof. What we can prove? How we can prove it? Let's consider fundamental sequence in space of bounded operators. So by definition, for any positive epsilon, there exists n capital number depends on epsilon, such for any nm sufficiently large, we have inequality by this. We know that this is supremum, yes? So we immediately obtain that for any x from the space x, a n x minus a m x less than epsilon multiplied on x. So we immediately obtain that this sequence is fundamental in space Y. And we know that Y is a Banach space. So we can conclude that there exists a limit as n tends to the infinity. And we know that this limit depends on x. Yes? And we know that the limit preserves the linear operations. Operator an is linear, limit preserves linear operations and depends on x. So it is linear operator the active connect. So this limit is some linear operator, some linear operator. So as usual, when we prove the completeness of the space, first we obtain the limit object, the limit of fundamental sequence in more weak sense. It is not uniform limit, it is pointwise limit, yes? So we must show that it is uniform. It is uniform. Again, take this inequality. We know that for any n m large, sufficiently large, the following inequality valid. And take here limit for m tends to the infinity. We know that we have pointwise limit. We have pointwise limit, so we immediately obtain that the following inequality is valid. But we can change this inequality on the non-strict inequality. Then take supremum, take sub for x equals to 1 and take immediately obtain. So uniform convergence. And here we have only pointwise convergence. But we show that indeed we have a uniform convergence. And then it is easy to show that operator A is bound. Minus an plus an, and then triangle inequality. It is less than epsilon for n sufficient large, and this is for any is bounded for any n. So we obtain that the norm of operator is finite. So we obtain that the norm of operator is finite. That's all. What is the profit from this theorem? Let X is normed space or field K, which is R or C, and consider all bounded operators from X to the field. It is all bounded operator from X to the field. Field of real numbers or complex numbers is a norm space too, with norm the absolute value of the number. So it is partial case of operators, but it is very important case. So this space has such notation. It is adjoint space. Adjoint space. Adjoint space to X. And elements of X are functionals. So it is partial case of operators, yeah? Partial case of operators. I define the functionals with small letters. F belongs to the adjoint space, and the norm of element F is supremum, for example, because we know that the norm in Y is the absolute value, so we can write, for example, such, or classical definition. Or you can take supremum not on sphere, but on the ball. So corollary from the previous theorem is Banach space. for any norm space X. Because all fields, real numbers or complex numbers are complete, yeah? So let's try to obtain descriptions of adjoint spaces for some concrete non-spaces. So theorem 1. T0 star adjoint space is isometric isomorph. We have that it is isometric isomorphism for L1. Isometric by this symbol. What it means? For any f from this space, we have one-to-one corresponding to element y from this. The formula for the functional is the sum x k y k x from 1 to the infinity. So we have an analytical description of our function. We have an analytic formula, and the norm of f is, for example, from this space, coincide with the norm of element y in L1. So for functionals, we have in concrete space, we usually have more convenient method to calculate the norm. If we know the isomorphic space, proof of this. First, let y is from L1 and construct functional f with index y, which acts on element x as in theorem. It is linear because sum is a linear operation. And let's try to obtain estimation on this action. By triangle inequality, when we put the modulus here. And then what we can do? We can take away from the sum the supremum for all xk. This is just the norm of x in C0, and this is just the norm of sequence y in L1. So I don't write, but of course, this is correct. Then what? But we must show that the norm, so by these estimations, we obtain that the norm of functional Fy is less or equal to the norm of sequence y from L1. Yes? If we take the supreme for all over x from the unit sphere, for example. But then consider consider the following elements. Signum y1, signum y2, signum yn, and then 0, 0, 0, 0. Of course, it is from C0. It have a limit of 0, and the norm of this element is equal or less than 1. We don't know about sequence yk, but it is not, signum is the absolute value of signum less or equal to 1. Then fy of xn just equal to this partial sum, and it tends to the whole sum as n tends to the 0. So by this estimation and this property, we immediately obtain, we can conclude that the norm of functional in L space as an adjoint space is just a norm of sequence y in L1. So this step is finished. So for any sequence y from L1, we can construct a linear bounded function. The inverse step, let f from C0 star. We know that such vectors 0, 0, and on cath place 1, 0 is a basis in C0. We know we have such task and we solve it. Define yk as value of our functional on the basis elements. If we take x, x1, x2, xn, etc. from the C0, we know that the partial sums tends to the x. Our operator is, our functional is continuous. So we obtain that f on the partial sum must converge to the value of functional f on x. But this equals our operator is linear, our function is linear, and by definition of the sequence yk, we obtain that this partial sum looks like this sum, the action of our function. So it tends to the, by definition of the limit of the partial sums, it's all sum. So we obtain the description of our function. Sorry, not correct here, not ek, but yk. So why? You know that our functional is bounded, so its norm is finite. and this norm equals to this. It's a problem all over ball, but it is greater or equal the result of action of our functional on such sequence. We can take absolute value, and this is equal to and we can take it, we can do it for any n nature. The left side of our inequality do not depends on n, so take limit for n tends to infinity, and so it means that sequence y belongs to L1. And again, in first step, we just show, we have shown that in first step, we show that norm of Fy just coincide with the norm of element. Let's consider some examples. Find the norm of the functional in C0. By theorem, we can see that yk equals 1 over 2 powered k. So the norm of functional is just this sum. And we have the answer 1. Okay. So let's prove theorem 2. Let parameter p is so, then LP star joined to LP is isometrically isomorphic to the LQ, where 1p plus 1 over q equals to 1. So it is again isometrical isomorphism. Isometric isomorphism. For any functional f from LP star, we have one-to-one correspondence for sequence y. Such that for any x from LP, f acts on x as the sum, and the norm of f LP star equals to the norm of LQ. Okay, the proof, the following. First, again, the scheme the same as the theorem 1. Only the norm, we can consider another norms. Let y from LQ construct functional f sub y on x equals the sum xk yk k equal to from 1 to infinity for any x from LP. It is a linear functional, of course, because the sum is linear operation, and then again try to obtain estimations. What inequality we can use here? What inequality we can use for this sum? Again, put the absolute value inside, and then use Hölder inequality. It is for 1 over when p is not 1, and it is less than if p is 1, then q is infinity, so it is for p equals to infinity. So by Hölder inequality, we obtain that in any case, we obtain this inequality is less than norm of L in LP multiplicated on the norm of Y in LQ for any. So we know that for P which is not 1, the Hölder inequality is precise, so we can take if 1 take xk equals to yk q minus 1 on signum yk. And from the Hölder numbers for the for adjoint for Hölder inequality numbers, we can obtain what? 1 over p equals 1 minus 1 q minus 1 q. So q equals so if we take xk pi, then it is equals just to the, so x lies in L pi. And for this, what we obtain and if I write divided, we calculate that the powers of xk powered in p equals to the q powered of uk, yk. So it is so for arbitrary x, we obtain the inequality, and just we construct the x for which we have equality. So by 2 this, we obtain that the norm of this functional just the same value as the norm of sequence y in LQ. But we consider only pi when we p not 1 for p equals to 1, we have q equals infinity. So the norm of y is supremum of yk. So situation A, exists such index k0 such that the absolute value of this coordinate just gives us the norm. So the situation of this when the supremum is maximum. So take x equals to 0, 0 on cut 0's place, put the signum of yk0 and then again 0, 0. Of course, the norm of x equals to 1, and f on this x just equals to yk0, equals to the norm of y in L infinity. And situation B, the norm of element y is not maximum, then there exists the subsequence of indexes kn such that absolute values of ykn tends to the supremum. Then take xn equals to 0, 0 on kn place we put signum of, and then again 0, 0, 0. And the norm of this element in LP equals to 1, and f of xn equals to absolute value of this coordinate, and it tends to the norm of a sequence y in L infinity as n tends to the 0. So all these calculations show us that the norm of functional fy equals to the norm of the sequence y in LQ. So we construct one correspondence for arbitrary sequence from LQ. We construct the function. Inverse step. Inverse. Let f is from LP star is a bounded functional, continuous functional. We know that ek equals to on the cut place for k natural is basis in LP for these parameters p for the finite. Then for any x from LP we have representation xk ek, where x equals to x1, x2, and so on. And we know that the partial sum tends to the x as n tends to the infinity. Define yk as the result of functional f on the basis elements. We immediately obtain that f of xk ek, the finite sum, tends to the action of our functional f on the sequence x, but this is by linearity of our functional is the partial sum of the form. So it is tends to the so we obtain the description of our function. Our function is the sum. So again, the question why is from LQ? Why this is from LQ? Again, different situation when we consider p from 1 to infinity. Take we know that our operator is our function is bounded, then it is equals supremum of all actions I take. The more general situation for x and x not 0. Of course, I consider non-zero functional. So if f is not 0 functional, then of course the sequence y is not 0. And take the x star equals to such sequence x1 star, x2 star, xk star, and so on, where xk star equals ykq minus 1 on signum yk, and then 0, 0, 0. So let's take away stars and put here n. And then construct the finite sequence xn, and xk equals to yk signum yk for the k equals 1 to n. And it is it equals to, recalculated, it is just uk yk q divided on ykq, but here the power 1 over p and the sum up to n. And it is equals, go here, it is just one over q, and it is valid for any n nature. So take limit for n tends to infinity, when obtain that so the sequence y belongs to LQ. Belongs to LQ. And situation B, when P equals to 1, so we must show that sequence Y is bounded. So it is from L infinity. So it is from L infinity. So take xn equals 0, 0, signum yn, the norm of xn in L1 not less or equal to 1, and the result of xn is just the absolute value of this. And of course, the fxn less than norm f. So we obtain that for any n, the yn less than norm f. So the sequence Y is an L infinity, and in step one, we show we show that this sequence is from LQ in any situation. So our functional f equals to fy. We show it here. Just so this means that our functional f equals to fy as in first step, and we know that from step one. One would know that norm of the equality, which just show the inequality, but we know that the equality. So that's all. And what corollary? All spaces LP are complete because they are adjoint space to the corresponding space. But LP small is the partial cases, it's partial situation for the spaces for LP capital. I give this theorem without proof. Theorem. Let omega m mu measurable space. Mu is sigma additive. Measure and sigma finite. 1 less or equal to p is finite, then LP omega mu is isometrically isomorphic to the LQ. Where 1 over p plus 1 over q equals to 1. And what it is isometric isomorphism? For any functional from this, let's take great capital, the capital G, one-to-one correspondence function G from this element G from LQ, such that for any function f from LP, G capital on f is just an integral, Lebesgue integral, and the norm of this functional from LP star just equal to the norm of function G in LQ. This is isometric. It is theorem 3, yes, but without proof. again, we have shown two steps. One step is easy with Gölder inequality, but in the inverse situation, to construct the function g, we need Radon-Nikodym theorem from the theory of real analysis of integral Becker. I decided to not to prove it. So, but you can use this theorem. You can use this theorem for the finding the knobs.